But we still have another representation that I told you before, which is actually more closely connected to this one, which is that we can take any function, scalar function, defined on this, and represent it as a column of 3 functions, all of them just defined in fundamental domain. But before I do this, I should remind you what is action of a group on a function. For some reason, this apparently was explained by Wigner in 1930s. You would think that this is ancient. And the idea is that if you have a function, and if you change the coordinates, you can think of this as just changing the coordinate, and then you evaluate that function at that coordinate. Because it's a scalar thing, but it's defined over the whole field, so the action should be just coordinate change, changing its argument. So the convention is to say that if I have a group element acting on a function of x, now this is now an operator, meaning it's defined by operational. The conventional definition is that this is same as inverse of the group acting on the coordinate, and it's doing it by this 2-dimensional matrix representation. Okay, so now let's repeat the trick of what we did in 2 dimensions, but we do it for 3 dimensions. So one thing that I can do and compute on this domain is, I'll call this rho of 0. I can take my function and compute it on fundamental domain. Then I can evaluate its image after 1 rotation, so G2, and its image after 2 rotations, and average. And I average it by the number of elements in a group, which in this case is 3. So that's obvious definition of symmetrized function on this space. Originally we had 2 pieces, we added them up and divided by 2. Now we have 3 pieces, we added up, divided by 3. Now what's the natural choice for the other 2 functions? Turns out I can have 3 symmetrizations using this group. I've divided, my original space has now become a vector of 3 functions, this, and that. So, write it out for you. Here I'll be lazy, I'll write 1, 3. There'll have to be some combination of these things. The question is, what's a good combination? And this is okay. Now, I can give these guys pluses and minuses, that won't work. But if I think about it for a little while, I can define omega, which I defined there, but I'll write it again. Cube root of unity. And I can stick here omega square. And here I'll say omega and omega squared again. And then I'll show you this mechanism. So now what I've done is, I've taken my original function, look at it only on fundamental domain, set of state space points only that live in this part. And I've written it as a sum of 3. However, in this case, alpha goes over 0, 1, 2. This is the label. So this is going to be called irreducible representation label. where rho alpha, evaluated in fundamental domain, is an average over all group actions. There are 3 group actions, and I'm averaging over the reactions. So I apply them and divide, so it's a sum over all group elements. And then each one of them has a number. And that number depends in which row here I am, in which irreducible representation. Here I'm just doing it for one irreducible representation, and depends on a group element. So there's the first group element, second group element, third group element. And then we have a function in that image of the elementary tile, where the character table looks like this. There are 3 group elements: identity, omega or G2, second repeat of that, and there are 3 representations. They're labeled 0, 1, 2, and 0th representation is just an average. So this number, character here, this number is just unity, and it's always like that in symmetric representation. It will turn out that in most applications we care about the symmetric representation most because that's like a ground state. This is the version of the function with least features because we averaged over everything. Then the first guy always shows, identity always shows with ones. And now the weight here is, and remember these are just cube roots of unity. And this one is omega square. And omega to the 4th power is omega cubed times omega. Omega cubed is 1, so that's just omega. And we can be a little bit fancier. We can use the definition of what we mean by group operation on a function to pull out this group element outside of the function. And we can write this as a sum of projection operators alpha acting on our function rho of x tilde, where the projection operator alpha is a group average, and that will do both for a finite and continuous group. We'll always average over all group elements. So, because there is G order of them is this number, average over all group elements. And then we have the character alpha, which depends on a group element. And then we have this operation. So this is now operator. So acting on a function, it'll rotate the coordinates of it, and it'll reproduce what we have here. Now, why do I call them projection operators? This is 2. So what I do is they're complete. So if you take sum over all representation projection operators alpha, the unity. And you can see it in this example. If I look at the coefficient, if I sum up the 3 functions, look at this coefficient, I will be looking at and what this is easiest to understand in argon plane. So you have a unit circle. These are roots of unity. this point is omega, this omega to the 0 power. This is omega to the first power, one turn, omega to the second power. And sum of these three vectors is 0, because they average on a circle. And there was the second column. If you looked at the third column, the third column is this plus that. Well, that's the same sum, but you can write it. So it's omega squared to the kth power. And when you work it out, that's 1 plus omega squared plus omega. Same sum. Equals 0. So the completeness is immediate. These projection operators resolve unity. They're orthonormal in the sense that if I apply one of these operations to my function, for example, I anti-symmetrize it, and then I try to symmetrize it, I'll get 0 because anti-symmetric thing doesn't have anything symmetric in it. But if it's the same operation, if I symmetrize something and I symmetrize it again, it's always symmetrized. So it won't make any difference. And I have to write no sum on representation label because I often have a rule that repeated indices are sent. Now, the reason why you know this is because generalization to Cn is immediate. That is, if I have a circle and I divide it into n neighborhoods, and this is n minus 1. So I have a propeller with lots of blades, like a shaver, a razor shaver or something. But still asymmetric. I cannot flip it, that it has an orientation. Then the same logic goes through, and you just find out that in that particular, for that kind of theory, these characters are just e to the 2 pi over n, and then they're labeled by k, which we call momentum label in usual application, especially in continuum. So that's where the characters are. And then you have a function. And you sum over that. And you divide by the number. That's actually a discrete Fourier transform. If you let n go off to infinity, you can rewrite it as a usual continuous Fourier transform on a circle. So this is discretization of Fourier transforms. And for them, you know that they're orthogonal, that each Fourier component is orthogonal to all other ones. And in this very simple situation, all the representations are one-dimensional. So you go from a vector of n functions, fundamental domain, and evaluate it on all its copies. That's representation of the function. And it turns out that you can rewrite this as n Fourier modes, which are mutually orthogonal.